Section 10.4 Areas and lengths in polar coordinates. Let R be the region illustrated in the figure, bounded by the polar curve r equals f of theta and by the rays theta equals a and theta equals b, where f is a positive continuous function and where b minus a is less than or equal to 2 pi. Then the area of the polar region is the integral of half r squared d theta. And this should sort of make sense because if you have the area of a circle, remember that's pi r squared. And if you want, let's say, the area of a semicircle, that would be half of pi r squared. You could think of that as 180 for the angle that a semicircle makes out of the entire angle that you could have in a circle, 360 degrees. You could also think of that as pi radians out of 2 pi radians times pi r squared. All of those are half pi r squared. It should also make sense then that the area for a quarter circle would be 90 out of 360, 1/4 pi r squared, or in radians that would be pi over 2 over 2 pi times pi r squared, which just leaves you with pi r squared over 4. So in general, the area of a sector of a circle, it shouldn't surprise you, is whatever angle you have out of 2 pi, because it's your fraction of your circle out of 360 degrees, times your entire area, pi r squared. So this means that the area of a sector, well, the pi's will cancel. They just basically leave you with half r squared times theta. So if we look at a tiny little piece in our picture with a tiny little angle d theta and some radius r, then it should make sense that the area of this tiny little slice of our region would be half r squared d theta. And then you would just sum up all of these little slices until you get the area of the entire thing. So taking that Riemann sum converts into an integral, and we get the integral of half r squared d theta. So let's do an example by trying to find the area enclosed by one loop of the four-leaved rows r equals cosine 2 theta. So we drew this in example 8 in section 10.3. So let's try redrawing it. So it looked something very roughly like this. We had 4 loops. It's supposed to be symmetrical. Wow, that one was terrible. That one was not much better. Okay, I don't know what happened to the left side of that one, but so this is r equals cosine 2 theta. I would like the area of one of these loops, so how about this one? So this loop, it looks like it goes from theta equals pi over 4 to theta equals minus pi over 4. So that means that we can write the area as the integral from minus pi over 4 to pi over 4 of half r squared d theta. So that's half of the integral from minus pi over 4 to pi over 4 of cosine squared 2 theta, because r is just cosine 2 theta. So then we integrate from 0 to pi over 4 because it'll be a little bit easier, right? All we have to do is double our integral. So I'm just going to look at this part. It's symmetrical. So I go from 0 to pi over 4, I double that, and then I get the whole thing. Doubling it cancels out my half, and I have an easier integral to work with. So I'll write this as the integral from 0 to pi over 4 of half of 1 plus the cosine of 4 theta using my half angle identity. So then I integrate, or I take the antiderivative, and I get theta plus 1/4 sine 4 theta using a quick mental substitution. And I evaluate that from 0 to pi over 4, and we end up with pi over 8. Let's now try finding the area of the region that lies inside the circle, r equals 3 sine theta, and outside the cardioid, r equals 1 plus sine theta. Okay, so we drew the cardioid in example 7 in section 10.3. So let's see if we can redraw that. So we've got roughly something like that, very roughly. And this is r equals 1 plus sine theta. Here's our origin. And we need r equals 3 sine theta now. So let's do that in another color. So that would be this circle. Okay, it's roughly a circle. We would like the area in between these two. So that means that we're looking for the area inside the circle and outside the cardioid. So that would be, this is what we want. So it looks like what we have to do is find the area inside the circle and subtract out this area over here inside the cardioid. Okay, so it looks like we need to see the area of the circle from here to here. So how about we draw a little raise? We would like to see what the theta equals for this ray and what the theta equals for this ray. So how about we try setting these guys equal to each other to see where they intersect. So we have 3 sine theta equal to 1 plus sine theta. So that means that sine theta must be equal to 1/2, because we just subtract sine theta and then divide by 2. So that means that theta must be pi over 6 or 5 pi over 6, because we're only going from 0 to 2 pi. So that means that this is theta equals pi over 6, and this is theta equals 5 pi over 6, which makes sense even looking from our drawing. So our area is half of the integral from pi over 6 to 5 pi over 6 of 3 sine theta squared d theta minus half of the other integral from pi over 6 to 5 pi over 6 of 1 plus sine theta squared. So this one is our green circle, and then this one is our cardioid that we're cutting out, and we're left with the area in between them. So what I could do is, instead of going all the way to 5 pi over 6, I can make my integral simpler again by symmetry. Instead, I could just stop at over here at pi over 2. So I could just look at this area and then double it. So I'll double my integrals, and I will change the upper limit of integration. So I'll still go from pi over 6, but I'll stop at pi over 2 now. And that way I don't have to worry about 5 pi over 6. So I square 3 sine squared, and I get 9 sine squared. And then I do the same thing with my other integral. And I end up with 1 plus 2 sine theta plus sine squared by foiling. So let's see, we end up combining our integrals. Our 2 cancels with our half, and we have pi over 6 to pi over 2 of 8 sine squared minus 1 minus 2 sine. And let's see, we can keep our 2 sine, we can keep the 1, but 8 sine squared we can rewrite. Remember that we have a half angle identity for sine, where sine squared is half of 1 minus cosine 2 theta. So that means that this integral can be written as the integral from pi over 6 to pi over 2 of 3 minus 4 times cosine of 2 theta minus 2 sine theta. And we take our antiderivative, and we get 3 theta minus 2 sine 2 theta plus 2 cosine theta, evaluated from pi over 6 to pi over 2, which is just exactly pi. Pretty cool. That area is exactly pi. So one issue that you can see that we might run into when doing these problems is finding the points of intersection. As we saw last time, finding where these guys are is pretty crucial, because otherwise you don't know where you should integrate from. You also have to switch your integral, because one curve might be on the outside between some points of intersection, but then it might switch between other points of intersection. Over here, the circle was on top, but if we had done our integral from here to here, then the cardioid would have been on top. We would have had to take that minus the circle. So let's see if we can do it in a more complicated example, where we have our r equals cosine 2 theta, which is our 4-leaf rows from the previous example, and our r equals half the circle. So let's try drawing our 4-leaf rows again. Really should just copy and paste it. Yeah, especially if I'm going to come out that bad. Alright, 2 down, 3 down, and I think that's 4. Okay, and we need a circle. So first let's label this r equals cosine 2 theta, and let's get our circle. That'll be r equals 1/2. So we're looking for points of intersection. So it looks like we're looking for all of these guys. So let's set these things equal to each other. Cosine 2 theta equals 1/2. That's when the two r's are equal. So that's going to be when 2 theta is equal to pi over 3, 5 pi over 3, 7 pi over 3, 11 pi over 3. So solving for theta, we get that theta is equal to pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. And notice we stopped over here at 11 pi over 3 because we're only going from 0 to 2 pi. So this means that we get points, if we plug in theta, we can figure out what cosine 2 theta is. So actually we don't even have to, because if they're intersecting, then that means that the r values must be the same. So they must all have an r value of 1/2. So we get 1/2 pi over 6, 1/2 5 pi over 6, 1/2 7 pi over 6, and 1/2 11 pi over 6. So these are all of our intersection points. I might as well try to be consistent. So that's over here is half pi over 6. And then over here is half 5 pi over 6. And then over here is half 7 pi over 6. And over here is half 11 pi over 6. But that's only 4. And it looks like from our picture there should be another 4. Should be these 4 also. There should be 8 intersection points. So let's see if we can figure out what those other 4 intersection points are. Well, it looks like by symmetry, if this guy's at pi over 6, then this guy should be at pi over 3. Similarly, this one should be at 2 pi over 3, and 4 pi over 3, and 5 pi over 3. However, where did these missing points come from? Well, we set cosine 2 theta equal to a half. But r equals a half is only one possible equation for our circle. We could have also done r equals minus a half. Remember when we drew our 4-leaved rows? Half the time when we were drawing our 4-leaved rows, we had to reflect because we would end up with negative r values. So we have to accommodate for those when looking at points of intersection. So the other 4 intersection points are half pi over 3, half 2 pi over 3, half 4 pi over 3, and half 5 pi over 3. And you can find them either by setting cosine 2 theta equals to minus a half, or by just looking for symmetry the way we did. The length of a curve with polar equation r equals f of theta, where theta is between a and b, is the square root of r squared plus the derivative dr d theta squared. To prove this, we use parametric equations. Let x equal r cosine theta, y equal r sine theta, and then we find dy d theta and dx d theta using the product rule as we have in the past. So derivative of this guy times this guy plus the derivative of this guy times this guy, and that's dx d theta. And then similarly for y, we get dy d theta. So then we take dx d theta squared plus dy d theta squared, because remember that for parametric equations we already have this formula where the square root of the derivative squared is the length when we integrate. So we just take the derivatives, square them, and add them together and see what we get. So squaring dx d theta gives us this mess. Then squaring dy d theta gives us this mess, because when you square these guys you have to FOIL. So let's see what cancels here. We have dr d theta squared cosine squared plus dr d theta squared sine squared. So sine squared plus cosine squared is 1, so when we factor out dr d theta, we get dr d theta squared times 1, so that's just dr d theta squared. Then we have minus 2r dr d theta cosine theta sine theta and plus 2r dr d theta sine theta, so these cancel. And then over here we have r squared sine squared and r squared cosine squared. So we factor out r squared, we get r squared sine squared plus cosine squared, which is r squared times 1. So it's just r squared, and there we go. So it's not that hard to prove, assuming that you already have the formula for parametric arc length. Alright, so we drew this cardioid a couple times already, so I'm not going to draw it again. Instead, we know that we're going to go from 0 to 2 pi, and we get an entire one tracing out. So let's integrate from 0 to 2 pi for our arc length of the square root of r squared plus dr d theta squared. And that's going to be equal to the integral from 0 to 2 pi of the square root of 1 plus sine theta squared plus our derivative of 1 plus sine theta, which is just cosine, so cosine squared. So that's equal to the integral from 0 to 2 pi of the square root of 2 plus 2 sine theta. 1 plus sine squared is just 1 plus 2 sine plus sine squared, and then sine squared plus cosine squared is 1, so we just have 1 plus 2 sine. So how could we integrate this? How about we try rationalizing it? So if we look at the integral from 0 to 2 pi of, how about we multiply the top and bottom by square root of 2 minus 2 sine theta. So then the top becomes the square root of 4 minus 4 sine theta, and our bottom becomes square root of 2 minus 2 sine theta, just multiplying numerator and denominator by the conjugate. So then I end up with our numerator as the square root of 4 times 1 minus sine. Oh, there should be a square there. I was like, I'm gonna take the square root, and it's a mess, but no, that'll be good. So I take the square root of 4 times 1 minus sine squared. 1 minus sine squared is cosine squared, so it's the square root of 4 cosine squared. So that's 2 times the absolute value of cosine. Do be very careful here. When you take the square root of something squared, you need the absolute value, otherwise your integral will be all wrong, especially in this case. So we keep 2 minus 2 sine theta in our denominator, and we have to be a little bit careful here because cosine, when we take the absolute value, it needs to be split where it's positive and negative. So it's positive from 0 to pi over 2, negative from pi over 2 to 3 pi over 2, and then positive again from 3 pi over 2 to 2 pi. So I'm going to take this integral and split it from 0 to pi over 2. And I get still the exact same denominator. Then I will make it negative from pi over 2 to 3 pi over 2. And because this negative would cancel because I'm taking the absolute value. And then I'm looking at it positive again from 3 pi over 2 to 2 pi. And by splitting it, that forces cosine to always be positive over here so that our absolute value can be taken away. Okay, so let's do a quick substitution. It looks like we have something in our denominator that has a derivative in our numerator. So just let u equal 2 minus 2 sine theta. So if u is equal to 2 minus 2 sine theta, then du is minus 2 cosine theta, so I'll just put in a minus. So when theta equals 0, 2 minus 2 sine theta is just 2. Then when theta is pi over 2, sine of pi over 2 is 1, so we end up at 0 when theta equals pi over 2, and we have 1 over rad u. And then similarly, we have 0 pi over 2. At 3 pi over 2, we have minus 1 for sine, so 2 minus 2 is 4. And we have got our 1 over rad u. And then we have 4, and at 2 pi, that's the same as it was at 0, so that's 2. Okay, so then these are fairly easy integrals. You just get minus 2 rad u from 2 to 0 plus 2 rad u from 0 to 4 minus 2 rad u from 4 to 2, which is just 2 rad 2 plus 4 minus 2 rad 2 plus 4, which is 8.